an Euler path is a path that uses every edge exactly once. I mean, have to travel all the edges, but exactly once, meaning that I cannot retrace the same edge. And an Euler path, if it starts and finishes at the same node, then it's going to be called Euler circuit. So let's start with this graph and see if in here we can find an Euler path. An Euler path can start and finish anywhere. The conditions are that should travel all the edges and exactly once. So for instance, let's look for a path from A to B, say. So we need a path then that starts at A, finishes at B, but with these conditions that travel all the edges exactly once. Let's start from A. From A, I can go to E, I can go to B, or I can go to C. These would be the three possibilities, right? I could go even to B because remember that in our definition of path, I could repeat vertices. I could come back there even if that vertex is the final one. So I could choose any of these ones. So let me start with this choice. I'm going to start with the path, with the edge from A to C. And then in C, now I have some choices here. I could go to B, I could go to D this way, or I could go to D this way. I will choose any one of these three choices. Let's see, for instance, that I choose from C to D this way. And so from D now, I have some choices again. So I could go to C, I could go to B, or I could go to E. I choose one of these choices. Let's say that I choose to go to B this way. And of course, I'm not done here, even if I write to B, because I'm after a path that travel all the edges. So far, I travel on only these three edges. So I keep going. So I could go now from B, I could go to C, to A. These are the only two choices. I choose, for instance, to go to C, like this. But then, once that I'm in C, I have only one choice here. I can only go to D. So I will go that way. And once that I am in D, I have only one choice now. You see that now as we go, we have less and less choices. So I have to go this way. And now from E, I have only this way. And now from A, I have only this way. And I am at the goal of my path. So I was able to find then an Euler path from A to B in this graph. Let's try to find now a path from, for instance, an Euler path from C to E, let's say. Let's see if we can find that. From C, let's start this way. I mean C to A, for instance, and I keep going. From A, let's say I take this one, and so I can go like this one, and so this one, and so this one, and so this one here, and so this, and I'm stuck here. You see that here in this one, I have no other place to go, and I didn't travel this one. So that means that my orange path was not a good choice for an Euler path. In fact, we didn't find yet a path from C to E. So let's keep in mind then the result that we are getting so far. I mean, we did find originally a path, an Euler path from A to B, and we were not able to find, well, at least this one didn't work. We can try others and see if we can find an Euler path between C and E. Try it. In fact, this problem that we are trying to solve, I mean, given a particular graph, there exists an Euler path, there exists an Euler circuit in it, was a problem that was posed for the first time by Euler in the 1700s. And this is the problem that he was trying to solve. This is a print of the town of Königsberg in Germany. that in the 1700s they have this problem. I mean, as you can see here, there was some people here that was just strolling the town, and see how the town is layout. So there is a river, there is like an island here in the middle, and there are some part of the town in this side, some other part of the town in this side, and more part of the town also here. And this river, I mean, to go from one part of the town or the other, there are certain bridges that you may see around here. Well, there are several there. You can try to find them. And so these people that was strolling the town have that problem. I mean, we're thinking, is it possible to stroll the town actually walking each of the 7 bridges that the town has, but without walking again in the same bridge? I mean, just walking once in each bridge. So that is what's called the 7 bridges of Königsberg problem, and that was what Euler set himself to solve, and he actually did solve the problem. So let's try to see if we can understand the actual problem. I made this other drawing just of the river and the part of the land here with the bridges that connect the different parts of land here. So Euler find a way to model this situation by a graph, by consider each of the part of the land that we see here like nodes in a graph. So let's call it, for instance, A, this part of the island, let's say, let's call B, this part here, and C, this part of the land here, and D, this part of the land here. And so these are going to be the nodes of our graph, and the bridges are going to represent the edges of the graph. So let's say that we have, say, A here in the middle, we have C, we have B, and so we have D here. And so the edges will be there will exist an edge if they are these 2 nodes, these 2 pieces of land communicate by a bridge or not. For instance, between C and A, we have a bridge, so I put an edge. But actually we have 2 bridges, so I put 2 edges here. And between A and B, there are also 2 bridges, so we're going to have here 2 edges too. And between A and D, there is 1 bridge, so I'm going to put an edge here. But between D and C, there is another bridge, so I'm going to put an edge here. And between D and B, there is also an edge. So this graph that we just draw is what is called the 7 bridges of Königsberg graph. And it's a multigraph. I mean, we have more than 1 edge between some nodes. And the question that Euler was trying to solve, we can translate in the language of graph by saying, is there actually an Euler path in this graph? Well, Euler did solve the problem, and in the way to solve it also proved some more general results. He actually proved that any graph has an Euler circuit if and only if all vertices have even degree. So he gave a complete characterization then of all the graphs that have an Euler circuit. So he said that they are going to have an Euler circuit if and only if all vertices have even degree. So that's the only thing that we have to check. If all the vertices have even degree, then we have an Euler circuit, otherwise not. And a little more general, we'll have an Euler path if we have 2 vertices with odd degree. So, of course, an Euler circuit is a particular case of Euler path, right? So then that's why we are including the case of having 0 vertices of odd degree or 2 vertices of odd degree. And in case that the graph contains an Euler circuit, so we are going to say that the graph is Eulerian. So with these tools, we can come back to the Königsberg graph, and we can decide if this one is going to have a path or not. So we just have to check the degrees of the vertices. This vertex, for instance, has degree 3. This one has degree 3. This vertex has degree 1, 2, 3, 4, 5. Okay, so we have a problem here. You see that we have a maximum 2 of degree odd. We have already 3. And this one also has degree odd. So this graph have too many nodes with odd degree. You see that? Remember that we have seen that the maximum that may have is just 2 vertices of odd degree. So in this case has more than 2 vertices with odd degree. So in this case we can say that no. The answer to the problem that Euler had is no. It's not possible to go around the Königsberg city crossing each bridge only once. It's not possible to do that. Now let's look at these two graphs. So the question is, are these Eulerian graphs? So remember that to be Eulerian, what has to happen is to contain an Euler circuit. And to contain an Euler circuit, because of the theorem, is the same thing that saying that all the vertices have even degree. So let's check. This is even good. This is even good. This is 4 is good. This is 2 is good. This is 3. Okay, so we are done here. So we have at least one vertex that is not even degree. So the answer to this is no. This one is not an Eulerian graph. So we know that it's not going to be way that we can find here an Euler circuit. But still, we could eventually find an Euler path. Remember that the condition for all Euler path is a little more relaxed. We can have until 2 vertices of odd degree. So in this case, we have 1. Let's keep checking. This one is odd, so that's good. And this one is 3. So in this case, we have exactly 2. So this one and this one are of degree odd. So in this case, it is going to exist an Euler path. Not an Euler circuit, but it's going to exist an Euler path. Let's find it. So let's try to find an Euler path, then starting at E and finishing at G. So let's start from E. Where we go? Well, in principle, we're going to go just to wherever we want. So I will go to A, for instance. So from E, I'm going to A. From A, where I go, they have no other choice to go to B here. From B, I have several choices we can choose. So let's say, for instance, if I go to E, I could go to E here. And then from E, I have only one choice. I only can go to F. And from F, I have several choices. Here I could go to G, to C, or to B. Say I go to B, for instance. I can go to B. And so after B, I have only one choice. I can go to C. And from C, I have several choices. I could go to F, to G, or to D. Let's say that I go to D. And so from D, I have only one choice. That would be G. And from G, I can go either to C or to F. So let's say I go to F, and from F I only have one choice, that I will be to C, and here the only choice to G, and I'm done. So this path that I put here is an Euler path. So there was not an Euler circuit, but there is an Euler path. In the second graph, let's check all the vertices one by one, and you can see that in this case all of them are even. So because of that, the answer to these questions are these Eulerian graphs. In this case, we can say this one, yes, it is. And we can try to find the Euler circuit that we know that it exists. And let's start in any node, and let's try to find a circuit that actually travels all the edges only once. I'll start, for instance, in D. I go D, E, B, F, D, G, F, E, G, B, D, G, and back to D. You may write down this sequence, but I did find then, in this case, an Euler circuit, right? Because this one, it is an Eulerian graph. Sorry, I put here path, but it should be graph, right? It is an Eulerian graph.